Hi, everyone. Welcome to the Global Ready Conference session, Research Revealed, the Impact of AI on Translation. I'm Alex Januszewski, Senior Director of AI and MT Solutions at Smartling.
And I am Mei Zhang, a Senior Data Scientist at Smartling.
Today, we're going to be talking about the major R&D updates and upcomings at Smartling. Before we get to the updates and upcomings themselves, we wanted to talk a little bit, because the session is based on the notion, what is the impact of AI? We wanted to do a brief introduction to LLMs, to talk a little bit about terminology, talk about where LLMs shine for localization, and May is going to talk about the top 5 use cases of LLMs. So things like fuzzy match repair, grammatically correct glossary insertion, edit effort estimation, as well as formality conversion and adaptive translation. And we'll conclude with sharing our research roadmap and some things that are working on that are very, very much future state. So when we talk about an introduction to large language models, I think for many people, what popularized the notion of large language models was ChatGPT, right? But in actuality, if you look at the slide, it's very illustrative, because even before ChatGPT, we had other large language models. So we've actually been having large language models for the last 4 or 5 years. What I find particularly interesting in this slide is if you look at the various dots that represent different language models and their parameters, there are easily over several dozen large language models here. And already this slide, which was at the end of December of last year, is outdated, right? We easily have over 150 large language models for different use cases for different languages. So the idea is how to make sense of them all. And hopefully we'll do that as part of our discussion today. So before we actually talk about large language models, we wanted to kind of do a level set and talk about terminology, right? So a lot of times, especially this is the case in the media, AI, artificial intelligence, and large language models, LLMs, and machine learning are all used interchangeably, all used basically as synonyms, right? And there's this notion of, hey, let's AI everything, right? As though this kind of magic genie comes out and fixes everything, right? From the standpoint of data scientists and computational linguists, that's not exactly the case, right? So we like to think of this as concentric circles, right? So if you think of AI as the broadest circle, it's essentially machines that perform tasks that are characteristic of human intelligence, right? That's the very, very broad definition. Within that, there are several different methodologies, approaches with how machines can do that, right? One is the first concentric circles, the idea of machine learning, right? It's the ability to learn without being explicitly programmed, right? And what we mean by that is that there are some older machine learning algorithms like classification, like regression, that don't involve large language models and are fit for purpose for very, very specific tasks, right? Then we talk about things like NN, neural networks, right? So the current generation of machine translation providers that you see out there, so for example, things like Google Translate, like Microsoft Bing, by and large, for their underpinnings, they're still using neural machine translation. The reason it's called neural is because it's modeled loosely after the human brain, the way humans work in our brain. And this does use deep learning. Now, the biggest difference when we talk about LLMs is very, very deep learning, right? LLMs are large language models with billions of parameters, as opposed to neural models, which may have hundreds of thousands, right? That's what makes them very, very powerful. So one of the things that we'll be kind of unraveling here is where neural language models are used and where large language models are used, what's kind of the best one for each use case. So also, people talk about generative AI, right? And when we talk about generative AI, we mean AI algorithms that can generate something, right? And that something can be images. You can see an example here where I give a prompt saying, here's a photo of a raccoon wearing an astronaut helmet, right? And you have something like DALL-E, which will create a picture for you, right? AI can generate designs, right? Architectural plans. It can actually write code. You see that in the screenshot as well. It could write music. For our purpose, we're going to be talking about generative AI as it applies to text, right? So things like chatbot, things like machine translation or smoothing machine translation, summarization, right? Everything that has to do with text. So I was mentioning different ways of having machines perform tasks that are similar to human beings. And when we talk about LLMs, where do they shine for localization? The metaphor that we're trying to use here is you have a diamond, right? Think of an LLM as a diamond, but you're not, even though a diamond may have the properties of cutting glass, generally speaking, you're not going to be purchasing diamonds and going around cutting glass with them, right? You can perfectly well use a glass cutter. And what we're trying to get at here is there are things that LLMs do quite well, like editing text. May's going to spend a lot of time on the different use cases for that. Chatbots, text summarization. However, there are a bunch of other tasks that can be done without an LLM that are still done as well as an LLM, ostensibly much faster and certainly much cheaper, right? So things like splitting a text into words, tokenization, doing part of speech tagging, right? If you think about your grammar trees from elementary school, this is a noun, this is a verb. Even though an LLM can do that, it's probably overkill to use an LLM for that purpose. So I want to talk now, since we've been talking about AI and LLMs, I want to talk a little bit about our North Star, right? So the idea of language AI, what we're trying to do is at every single step of the content lifecycle in our platform to infuse AI. So for example, beginning with intake automation, where we use AI algorithms to analyze customer content, to then optimize that source content. So rather than assuming that the source is good, what if the source is difficult? And it will be difficult for a human being, and then certainly even more so for a machine. What can we do to optimize, to correct that source, to make it less complicated? Also, can we identify that source and say, wait a second, this is, for example, marketing that's masquerading as online documentation. We need different resources for this. Then, of course, a lot of the things that May is going to be talking about, so things like machine translation, and then after that, all sorts of normalization or smoothing for which we use large language models. And then finally, once we formed and smoothed a machine translation, how do we estimate the level of effort so we can send signals in dynamic workflows to our translators and say, this is good, this is problematic, and here's something in between, right? And that allows us to be very, very efficient. And so that takes us into the AI translation toolkit, which probably you heard mentioned in a previous session. And what happens in the AI translation toolkit is now we're beginning to use LLMs pretty much for all step of the process, right? So in step one, content comes in, we first leverage your translation memory because we know that this is the gold standard, this is good, this has been published, it's been done by a human being. But can we actually improve it, right? Can we take a match that's a 70% match and turn it into a 90, 95% match so the linguist will be far more productive, right? And that would lead to cost savings as well. If we're not able to find a match, off we go to machine translation, which actually can be done either by auto select, where we're choosing the best of the generic engines, or with a customized engine where we've tuned an engine for you that has dramatic improvements in quality, sometimes as high as 30, 35% improvement in quality. Once we get the machine translation in step two, then we begin to do post-processing informed by LLMs. So things like glossary term insertion in a way that's grammatically correct. And May will be showing an example of that. And lastly, once we formulated the best machine translation that we can, we run edit effort estimation. So we can then dynamically reroute strings either to skip them altogether or perhaps to have one person or maybe two people, depending on how critical the error is. Our early findings from the AI translation toolkit are very encouraging. We see a 200% reduction in active linguist time. We see roughly a 15% decrease in the number of edits. And all of this is coupled with an MQM score of 98 plus when paired with human validation. So what we're seeing here is reduction in time, reduction in cost, yet the quality is the same and even better. So let me turn it over to my colleague May now, who's going to talk about very specific examples of LLMs.
Thank you, Alex, for that overview. Now we will dive straight into the research findings behind the features in the AI Translation Toolkit. We will also be discussing some R&D that are still in progress. Step 1 of the AI Translation Toolkit that Alex just mentioned is the AI Translation Memory. This is the step where large language model fuzzy match repair is applied to boost translation memory match and increase leverage. What do we mean by fuzzy match repair? Here, we will walk through the explanation with an example. Imagine you have a source text that you want to translate. In this example, we have, are you sure you want to delete this chat? This source text gets matched to a similar translation in your translation memory. Are you sure you want to delete this photo? Note that the only difference between the source you want to translate and what you already have in your TM is just one word. You want a new translation that includes the word chat instead of the word photo. This is where fuzzy match repair comes in. Large language models can be fed your TM as examples along with your new source text. It will then return a translation corresponding to the meaning of your source text while keeping the style and voice that's already in your translation memory. In this case, we see that this fuzzy match repair is correctly repaired to correspond to the meaning of the source text. Moreover, the conjugation of estar is correctly converted to ested to match the gender of the repaired noun. During the research stage, our task is to figure out not only which model performs the best for the repair, but also which one offers the best performance for the cost. Academic and industry research have shown us that providing large language models up to 5 examples yield the best results. Here, we experimented with a number of fuzzies ranging from 1 to 5. What we found is that across all the models compared, 5 fuzzies will yield the best results. Google's Gemini and OpenAI's GPT-4 are among the best performers with 5 fuzzies. In this figure, the percentage strings identical to target is referring to when the large language model generated a repair translation that is identical to the final translation. We use this metric as a proxy to estimate how much of the repair strings will require no edits when we release this feature to production. The more strings being identical to target means that on average, the edit rates will be lower. This is exactly what we are seeing in the middle section of this figure. The third section plotted on this figure is the cost. As you can see, GPT-4 is the most expensive model, while the cost of Google models are on par with GPT 3.5. What is interesting is that high cost doesn't always yield good results. GPT-4 with one fuzzy costs about 10 to 20 times more expensive than the Google models, but it is performing worse. Now let's take a look at the best performers. While GPT-4 and Gemini yield similar percentage of strings identical to the target and similar edit rates, Gemini is 40 times cheaper. The results shown here are for mainland China, but we have tested this on other locales as well, and the results are very similar. For fuzzy match repair, Google models provided the best bang for your buck. Now let's take a look at our large language model fuzzy match repair feature in production. We have deployed this feature for a few months now, and here are the results before and after large language model fuzzy match repair for our top 10 languages. Before the LLM-based fuzzy match repair, we have about 20 to 35% of strings without needing a human edit. These do not include 100% matches and are based on non-LLM fuzzy match repair approaches. After the implementation of the LLM-based fuzzy match repair, we are seeing about 45 to 65% of strings that have an H tail of 0, depending on the language. An H tail of 0 here means that when a repair string appears in front of a linguist, the linguist make no edits to it because it is already a perfect translation. Next up, we will discuss glossary insertion, which is part of the AI post-processing step. Let's illustrate it with an example. Here we have a source text, schedule your first post. The machine translation produces a translation that says programmer su primer post. However, the glossary states that the word post should be translated to publicación. Traditional approach to glossary insertion will result in a replacement of the terms, but not necessarily a grammatically correct sentence after the replacement. As you can see from this example, if publicación is replaced, the ordinal number primer should be conjugated to primera since publicación is feminine in the Spanish language. But this doesn't happen in the traditional glossary insertion approach. On the other hand, using large language models, you see that not only is the glossary term respected, but the resulting sentence is also a grammatically correct one. Now let's look at the results of the glossary insertion from two angles. First is from the perspective of coverage. When glossary insertion is turned on, we see up to 96% glossary coverage as compared to 65% of glossary coverage without glossary insertion. On top of the 96% glossary coverage, we are also seeing improvements in the quality of the insertion. We see that more than 75% of the strings are now morphologically correct with large language model-based glossary insertion, as compared to about 60% of the strings that are morphologically correct using traditional glossary insertion methods. And for high-resource languages such as Spanish, we see that the percentage of strings being morphologically correct can increase to over 90%. Here we have tested the two locales, Russian and Spanish, to represent the two very distinct language groups that they belong to. Next up is the edit effort estimator. This is the LLM-based estimator that tells us how much editing effort is required of the initial translation in order to turn it into a perfect translation. This estimator takes as input the source text, the translation text, and other metadata such as your content domain and the locales that you're translating into. It is currently available in our Smartling workflow, as you can see in the figure on the left. It outputs 3 levels of effort. Level 1 corresponds to the translation that will perhaps only need a review, whereas level 3 corresponds to translations that would require human edits in order to guarantee quality. With regards to the performance, our estimator achieved a 40% increase in accuracy above random guess for level of effort. And on top of the 40% increase, it achieved another 13% improvement in accuracy if you fine-tune the LLM with your data set. This is an area of active research that we are still working on and will continue to work on in order to improve its accuracy even further so that you can use it to route your workflows with confidence. Next, let's talk about something that isn't part of the AI translation toolkit yet, formality conversion. Before we talk about conversion, let's discuss what formality is. Here, I want everybody to think back to all of the wedding invitations that you have received before. The dress code that's listed on those invitations aren't just black tie required or beach casual. There is a whole spectrum of dress codes in between, depending on where the wedding venue is, what is the theme of the wedding, etc. It is the same when it comes to formality register. While people can talk about whether a sentence is formal or informal, formality is not binary. It is actually a continuum that depends on many factors. And I will mainly discuss 4 of these factors. First, it is the domain. User-generated contents usually sits on the informal tail, while more technical and legal documents sit on the formal end. Second, formality depends on the speaker and listener relationship. We see this a lot in the Asian languages, most notably for Japanese, right? When we're addressing families, young kids, people of lower ranks, it's more informal, as opposed to when we're talking to strangers, older adults, people with higher ranks, we tend to be more formal. Third, formality depends on the mode of communication. When I'm texting my friends, I tend to be more informal, where a lot of my texts are truncated and a lot of emojis were sent. But letters and invitations by mail tend to be more formal. Fourth, it is the intention of the speaker. It is more informal or familiar if you're trying to connect to your end users, whereas it is more formal when you're trying to promote high-end and or luxury brands and products. Lastly, it's not listed on this slide, but the language itself sits somewhere on this spectrum as well. If we turn formality into a score ranging from 0 to 100, with 0 being the most informal and 100 being the most formal, I would say that French is probably an 80 on that formality scale, simply because it's the language French. Due to all of these factors at play, what makes formality hard is getting the degree right. For example, usually for medical content, the Spanish translation guideline is to translate it using a formal tone. But during the COVID-19 pandemic, we see a change in the formality register in translation of medical advice when the government wanted to connect to its end users in order to get them to follow certain safety protocols, such as frequent hand washing and social distancing. Such type of content are then more appropriately translated using an informal tone, even though it is considered medical content. Because the terms formal and informal are not concrete, they are not specific enough for large language models tend to go overboard when you don't specify exactly what you mean by a formality conversion. For example, when you ask it for a formal translation, it can deliver an overly formal translation as if you were asking the queen out to dinner. On the other hand, it can also be overly familiar and tend to be strict slang when you ask it for an informal translation. Therefore, due to the complexity of formality, we narrow down the scope of our research to the task of a minimal formality switch. What that means is that when we ask the large language model for a formality conversion, our success criteria is a minimal conversion with proper conjugations of the affected verbs, adjectives, nouns, and other parts of speech that are affected. The words in the original translation that are not affected by the register change should be kept the same. What this means is that in the case of converting from formal to informal, the new translation should keep the original word choice as much as possible without replacing the original words with slangs, which will make the translation overly informal. And here are our results. Across all of the locales that we have tested together with our linguists, they all achieve a success rate of over 80%, with Spanish Spain being the most successful at 95% proper conversion. I also listed here the properties associated with the strings that often fail conversion. For Spanish, they are the strings that contain self-reflective verbs and a small percentages of the strings associated with the male gender. For German and for French, the failures are the imperative strings starting with the second person pronoun. For French, some strings also became overly informal due to the truncation of the second person pronoun with its associated verbs. So a main takeaway from our formality conversion experiment is that each locale would have different kinds of issues in the strings that are not properly converted. Due to this fact, it is important to note that there isn't just one universal formality prompt that will work across all locales, and we are still in progress to test out other locales together with our linguists. The last experiment that I'll be discussing here is the adaptive MT experiment. This translation option is for clients who want to train custom engines to get high quality translations, but don't have enough translation units in their translation memory to do a full-on custom engine training. Here we compare two competitors across 2 verticals and 6 languages. This resulted in 24 sets of scores for comparison. The quality metrics that we look at range across all automatic scores, ranging from blue to TER to media and blurt. The results show that Google Adaptive won 6 out of the 9 languages on vertical 1, and it won 2 out of 3 languages on vertical 2. Google Adaptive, on average, showed up to 23% increase in quality over competitors across the various scoring metrics that we mentioned. Here are our main takeaways. 1, adaptive MT is the only way to train an MT engine using LLM technology when you only have very little data in your TM. 2, Google's adaptive MT is very well suited for creative content. And 3, it is up to 2 times cheaper than competitors that offer the same functionality. So this concludes the research deep dives by the numbers, and I would like to thank all of my colleagues on the R&D team as well as the engineering team who contributed to these findings that Alex and I get to present here with you today. With that, I'd like to hand the mic back to my colleague Alex to discuss our research roadmaps and future research directions.
May spent a lot of time talking about what's already been released on our research roadmap. I just want to mention a couple of items that are in active research right now. So things like fine-tuning models for MQM prediction, because we see that fine-tuned models, much like customized MT models, do a better job than generic foundational models. We're also working on a high-performing auto MQM model. And one other thing that's quite important is the idea of letting customers choose their favorite LLMs, right? Because different customers, depending on their corporate policies, may be able to use one LLM versus another. So we want to make several LLMs available for the tasks that May mentioned, so we'd be able to support those customers. As far as something that's upcoming later, more protracted period for research, some of the things that what we're working on include expanding LLM language support, source content pre-editing. We touched upon the idea of making the source less complicated for the machine translation process. LLM content creation. So rather than translating, initially creating the prompt so the content would be created in the target language already, and making available some of our prompt engineering tools and our prompt engineering workbench as a playground for clients to test out their prompts. So a summary of the features we already have and that we covered. So we have in the platform LLM as an MT provider, the ability to do batch translations with an LLM, the research that May talked about that's in production right now, edit effort estimator, glossary insertion, fuzzy match repair, all 3 are part of the AI translation toolkit. Also, I want to mention that in addition to the Smartling platform, there is the Smartling Translate platform, where we're using LLMs that can rewrite translations by shortening, by rephrasing, or suggesting alternative translations. As far as features that are upcoming, some particularly interesting ones, I spoke about the idea of prompt engineering tooling and workbench. Adaptive translation, where via Google Adaptive, where we're seeing lots of very, very promising results. And the idea of using persona translation as part of an LLM prompt. So for example, if I'm translating for a particular audience, or I am trying to foster a particular business persona that's, let's say, more casual versus less casual, depending on the client, that's something that can be included in the prompt. May is going to conclude this session talking about a very interesting area of research, which is image context translation using LLMs. So May, I'll turn it over to you for the last couple of examples.
Okay, Alex, thank you. So here I will give some examples of very futuristic looking research that we're embarking on. And this is the examples that we have for image context translation. While Smartling already offers image context translation for linguists, we think that this is a task where LLMs will shine as well. Take, for example, the polysemous word palm. Without any context, we don't know whether this word is referring to the palm of your hand or to a palm tree that grows in tropical places. If, however, this word is embedded in an image, such as a picture of a hand or a picture of a palm tree, then the large language model can analyze this image and the associated text to give you the correct corresponding translation. Here we are prompting the large language model to analyze the image, provide an explanation of the image, and then translate the text within the image. And here's what it says. For the picture on the left, it's saying that this image shows a line drawing of an open hand with the fingers extended and the palm facing forward. Next to the handwriting, there's the word palm. And then it provides the proper translation of the palm of your hand in Chinese, which it says 掌心. And then if we take a look at the image on the right, the large language model says this image depicts a simple illustration of a palm tree with the word palm written next to it. The palm tree is stylized with a brown trunk and green fronds so that it spreads out to resemble the typical appearance of a palm tree. And then it says the word palm is likely labeling the illustration, right, which it gets correctly. And then it provides the proper translation for palm tree in Chinese, which is 棕榈树. So we think that large language models will shine at providing a good first translation, given that it is provided with the image context. Besides polysemous verse translation, it is also good at translating idioms when the image context is provided, right? Let's look at this example where we prompted the large language model to analyze the following image and provide a transcreation for the text inside the image. Here we use the term transcreation rather than translation because when we use translation, it tends to be more of a literal and direct translation, which is not what we want for idioms. So here we see that the large language model is able to properly analyze and interpret this image, right? It says the phrase break a leg is a common idiom in English, typically used in the performing arts to wish someone good luck before they go on stage, right? And it can come to that conclusion because it's able to know that this image depicts a cartoon style drawing where a human man is adjusting, these groups of fruits and vegetables that are, costumes. So here it's able to then properly provide a transcreation in Chinese that says 好儿子今晚出去好好表现祝你好运 the Chinese phrase 祝你好运 translates to wish you good luck and is used here instead of a direct translation of break a leg. This note is actually provided by the LLM2 to give an explanation of why it came to this transcreation rather than the literal translation of break a leg, because it says, the literal translation would not carry the same idiomatic meaning in Chinese and it would sound very odd or even alarming. So these are the two examples that we will end this with. Eventually, we hope that the large language models will be able to take these direct image translations and take into consideration all of the context embedded within the image and provide us with a direct image translation, right? These are just a couple examples of our future research directions. And with that said, we are still at the dawn of AI. And as we venture forth, we imagine a collaborative partnership between linguists and AI. Together, humans and machines will shape the future of communication, ensuring that it remains as vibrant and as diverse as the languages and cultures that they represent. Thank you.